minus 1/3 of 1 cubed minus 1/3 of 2 cubed minus parentheses minus 1/2 of 3 squared 4 squared minus 1/3 of 3 cubed minus 1/3 of 4 cubed. All right, which I could calculate, but that's not really the interesting parts here, right? Right here, right? Do you guys understand the idea here? So this is why potential energy is important, is it saves us the trouble of actually going through the integral. And sometimes we don't even need to know the curve. All right, so let's see here. I've told you about power. I've showed you an example where you can actually calculate one. I think the other thing I wanted to do today, oh yes, was a one-dimensional example. Let's see here, if I can. Where did I put my, oh there it is. Now, we need the vectors and the gradients and all that for 2- and 3-dimensional examples in general, right? Next week, as we get into examples with pulleys and planes and things, we'll have special formulas for gravity, which will allow us to get around some of this formalism, right? Which is why you could do physics in high school without some of this, right? Because there are special formulas for gravity and such. But also in one dimension, we can get away with some of this not mattering as much. So like, for example, if I have f of x equals to, oh, I don't know, I'll put the dimensional qualifiers back in here. Alpha x plus beta x squared, you know, I could find work done from x1 to x2, right? How would you do that?
Find the potential energy function.
Oh, you're like find the potential. Wow, that's hardcore. All right. So I was going to say you could just integrate, right? I mean, you're right. We could find the potential energy function, provided that this is a conservative force. Is it? Is this a conservative force? If you set this equal to minus du dx, can you find u? I think you're right. I think the potential energy here would just be minus 1/2 alpha x squared minus 1/3 beta x cubed, right? You're right. And so if I want to calculate the work done, which would be what? Minus the change in potential energy, yeah? So I could do it that way, you're right. So that'd be like 1/2 alpha x squared plus 1/3 beta x cubed. There's a minus on all that. My bad, I need to expand on that. I regret erasing that. So it's minus, it would be minus u of x1. It's messing with my head. Minus u of x2, rather, plus u of x1. So that's this. So there you go. That would be the work done. Yep. Alternatively, we could just have integrated, right? It's like to calculate the work done here. We integrate from x1 to x2 of f of x dx, which would have been what? Alpha x plus beta x squared dx. And it's not hard to see that that would give us, oh, look at that, guys. You see what I did? You guys are going to tell me about that, right? This one? Yeah, that's a 1. Yeah. But you can easily see that this integrates to give that, right? But we could just as well see it as minus the change in the potential energy. Fair enough. So, great. The story is less interesting in one dimensions in terms of finding potential energy, right? Because you just integrate. If you can integrate the force and then put a minus on it, that's the potential energy. Okay, so for example, I think I did this last class, but I'll do it again. I may not have. Hooke's law, right? F equals minus kx. Well, that's what? That's minus d dx of what?
K over 2x squared.
K over 2x squared, right? 1/2 kx squared. So 1/2 kx squared, u of x equals to 1/2 kx squared. This right here is potential energy for spring, which we'll talk a lot more about next week, of course, but there you go. Let me ask you a more interesting question. Can you analyze the motion for the force in example 4? Let me set alpha equals to 2. And let me set beta equals to 3. Here's my instructions. Analyze motion for the force alpha x plus beta x squared. How would you do that? So we need some tools that I haven't quite explained to you yet. Let's do that. And so it turns out we can analyze the motion by making a graph of the potential energy function. And if we do that, if we make a graph of the potential energy function, we can analyze possible motions. So I need to just mention a general theorem, which is this: if the mass times the acceleration is equal to a force which is just a function of x, all right, which is in fact minus du dx, right, then the energy, which is equal to 1/2 mv squared plus the potential energy u of x, is constant on the equation of motion. In other words, energy is conserved in one dimension. This is a consequence of we proved this in 3 dimensions last class. It's still true in 1 dimension. If you want to see the proof, you can watch my video from Calculus 2 this morning. We derived it in there, just in 1 dimension. What does this mean? This means that if you think through it, we can plot the motion using energy curves. Let me explain. Let me show you an example of this. I'll do a simple example before I do the complicated one, okay? So example 5, let's talk about the spring, right? Spring force. Spring force, F equals to minus kx, right? So what's the potential energy? Like we said, 1/2 kx squared, right? So if we plot an energy diagram, so here's the energy diagram, all right? Here's x, and here's u. We're going to plot the potential energy. This is pretty easy to do. For the spring, what's it look like? 1/2 kx squared, what's that? That's a parabola, right? Yeah, quadratic, right? That's just a parabola. It's something like this, yeah? So there you go. This is U equals to 1/2 kx squared, right? So now let me draw some different energy levels and talk about physically what's possible. See, because the energy is constant for a motion, right? Energy is constant. So if I'm talking about a motion, if this was the energy, let's say E1, where is the motion of the spring going to be? Think about this. For this to be energy E1, remember, is equal to 1/2 mv squared plus the potential energy as a function of x. So, in the regions where the green line is below the red line, that means the kinetic energy is negative. Is that possible? Can kinetic energy be negative? What's kinetic energy equal to? Remember? Kinetic energy, 1/2 mv squared, right? It can't be negative. So therefore, classically speaking, this motion over here is forbidden, classically. In quantum mechanics, there's something called tunneling that actually happens. There's an exponential decay of the motion outside of those classical boundaries. That's what semiconductor technology is built over, actually. But classically speaking, you can't go out there, all right? So what that means is the motion is bounded for that energy level between here and here. So that's how we analyze the motion. For a spring with energy E1, the motion is stuck between right here and right here. It's bounded between x1 and x2. What happens? The spring stretches out to x1, and then the spring pulls back and compresses back to it stretches out to x2, and then it pulls back and compresses to x1, at which point it pushes back to x2. And then it contracts back to x1 and back and forth and back and forth. That's the motion of the spring. This is how it looks like on the energy diagram, right? And the higher the energy, the further it oscillates back and forth, right? But anyway, this is motion of a spring. How would this analysis go for our example 4? So we've got, what did we say our U was? I said minus 1/2 alpha x squared minus 1/3 beta x cubed, yeah? And what did I do for us? I put alpha equals to 2, and I put beta equals to 3, which is kind of friendly, because that makes U equal to what? Minus x squared minus x cubed, which means there's hope for us graphing this, yes? Can you graph that? You can graph it, right? Well, you guys got graphing calculators, so what am I talking about? Some of you are solving quadratic equations with a graphing calculator in here. What's up with that? You guys are weirding me out. Like I get it, but goodness, there are easier ways. Let's see here. 1 minus x. There's like 2 or 3 of you on the test who get to a quadratic equation, you're using the graphing calculator and looking for the intersection of graphs to solve it, which, I mean, I've done that once upon a time, but it's so much, well, anyway, I'll shut up. Come talk to me in office hours. I'll show you a better way. Okay, so can you graph this? I mean, we can graph this, right? What's it look like? It's got zeros here and also at 1, right? It's a cubic. What's it doing? It's bouncing. Yep.
Shouldn't it be 1 plus x?
Oh, thank you. Yeah, thank you. Muchas gracias. Let's see here. Over there then. Thank you. Yeah, that was your comment at this moment in time is appreciated. 2 minutes from now, I would be like, ah. So thank you. Very good. So minus 1. So it bounces off the origin, right? And it's positive back here. So the graph looks something like this. Bounce. All right, this is the graph of U. So if we want to analyze possible I should have done that in red to make it like the other one, my bad. Color coding. There we go. All right. Now I've ruined this red marker. Oh well. So now if we look at some energy levels, for example, this energy up here, what's the motion at E1? What happens? Remember, the rule is that the kinetic energy can at most be 0. When the kinetic energy is 0, what does that mean? That means like you're at a place where you're turning around, basically. If the kinetic energy is 0, that would be like here. That's the furthest point it goes over for this particular energy level. And then there's interesting things that happen, right? If your energy level is right here, right? If this is your energy E2, then where your motion is depends on where you start. See? If you're starting here, right? If your starting point's x1, then you're just going to go back and forth in this potential well. On the other hand, if your motion over here is at x2, then there's different stories, right? If your initial velocity is to the right, you just keep going on and on and on, out forever, you never come back. If your velocity is to the left, then you're going to come in, you're going to hit the potential well, and you're going to bounce back out. So this is how we can analyze motion using potential energy. We draw the potential energy graph, and we think about energy levels, and that's how to do it. Listen, this is not in lecture 15, but I noticed there's a problem in your homework about it. I wanted to talk to you about it so you could think about it over the weekend. This is technically on page 3 of lecture 18 if you want to see where I blather on about it in the notes. But anyway, thanks guys. Have a good weekend.